we'll go. So I will first talk about Koszul duality in the first half or so, which may last about 40-45 minutes, or something around that. And then I will talk about higher categories in the second half. And also the first half is mostly is going to be about other people's work, and then the second half is going to be about my own work with Lazarev and partially Manuel Rivera. But let's start. And so yeah, the first part is supposed to be very comprehensible, not comprehensive at all, just comprehensible. So just stop me if I say things that don't make sense. You can also stop me if I go too slowly. So we start by the basic pattern of studying algebras via their modules. And I'm going to start very gently with two algebras I really like. So one is just the polynomial algebra with one variable over some field. So K is going to be a field. K can be C if you want it to be. K can also be a ring with some like a VID, like the integers at some places, but for simplicity, it's just work over a field, and then everything's going to be true without any caveats. Right, and so of course over A, there's sort of two kinds of modules that jump out at you. You can just take some number of copies, or you can quotient out some ideal. And so geometrically, if Kx is the line, I can have some infinite bundle, or I could have some skyscraper sheaf living somewhere. Another very nice algebra is my algebra B, which I'm going to write like this, which is got the dual numbers, K epsilon, but epsilon squared is 0. And I can build, I can also do this, I can also look at free modules over that. And I can also divide out by some ideas, but this is a very small ring, so there's not actually much happening. So I have somehow K epsilon divided by epsilon is somehow the really reasonable quotient of this thing. Right, so I have these modules over K epsilon. And now if I want to compare modules over two algebras, one good way of writing down functors is to write down bimodules. So I can use a bimodule. So we write A, X, B. So the left A module is the right B module to go between A and B modules. Right, so then this is A and B, some examples for A and B, but of course this is a very general construction. Whenever I have a bimodule, I get functors. So A mod to B mod, and the way I set it up, I get a junction going this way, so I can take my B module to tensoring over B to get an A module, and I can get my A module to take the hom over A from X to M to get a B module. Right, this was the right B module. I get the left B module structure as I take the hom out of it. And this is always a junction and sometimes equivalence. In which case it's called a monoidal equivalence. Or if, so I've been writing mod somewhat agnostically, if I want to look at chain complexes of modules or DG modules and derived categories instead of module categories, I could have derived notion of derived monoidal equivalence. And in fact, that's what I'm going to have to do if I want to find a nice bimodule connecting my two example algebras here. So my next task is to find a nice kx, k epsilon bimodule. So I'm going to give this guy a name, which is Ka. Well, it's the ground field, but x acts by A. So I can, one thing I could see is a sort of K0 or K epsilon mod epsilon. So just the ground field trivially is an action of, is a bimodule, but that loses a lot of information. That's sort of not very interesting. I could also just tensor the two things together. That gives me a bimodule. I just act by multiplication, but that somehow separates my two factors, like they don't talk to each other, so it's going to be a very boring functor. And the interesting functor one could write down is if I take kx epsilon and kx, but I put a differential on this, and then I get some complex with two terms, which is equivalent to K0. It's a resolution of K0, if you will. But as I take my tensor product as my home here, if instead of my trivial module K0, I use a resolution, I keep more of the information. So I have a derived adjunction here, which is better behaved. And I can nicely compare A modules and B modules now.
Is it a tensor product or a direct product?
So this was a tensor product.
Okay.
Yeah.
So it's resolution of K as a Kx.
So it's as a complex, K naught as a complex. But in fact, if I act by Kx on the left and on the epsilon on the right, it's also compatible. So it's a bimodule resolution.
Right.
Okay. So if you will, I'm just sort of saying, well, I can take the first module that I thought of, but then I just divide these factors. I'm just sort of saying I take a bigger module which keeps more information, but because of this differential, I'm sort of boiling it down back to K0. And right, so let's do this in this example, and one can do some computations, which I'm not going to spell out, but which you can really sort of go away and do. So I'm going to put the DG here now because I'm looking at chain complexes of modules because I resolved my bimodule. So I have to be in some category of complexes for everything to make sense. And here I have my K epsilon modules. And so I take Kx and I take the home over Kx of Kx epsilon and epsilon of x. That maps to Kx. So this is my module here, which is a free module. And I'm in this situation where I take my module M two homes out of the bimodule into the module. This is my bimodule. This is my module. And Kx means that essentially I just get two copies of Kx, but then this differential here induces a map between the two maps, between the two modules. And so this is going to be itself a resolution of, is quasi-isomorphic to K, and as a module over epsilon over K epsilon is exactly K epsilon over epsilon. So the one-dimensional module where epsilon is trivial. So I sort of take my free module here and I send it to this trivial module. And I could also start with my trivial module K0, Kx divided by x, and I do the same computation. And that is now sent to the free module over K epsilon. And I go backwards. Right, I start with K epsilon here. And I'm going to be sent, I tensor with this gadget, and I unravel, and I essentially get the gadget back. Because I tensor over K epsilon with this K epsilon module with K epsilon, so I just get the module back. I'm going to give the module a name called K, stands for Koszul. And so this just goes to K itself, which is equivalent to K0. So I'm identifying quasi-isomorphic things, identifying things resolutions with the things that they're resolving. And similarly, if I start with my trivial module here, I'm going to end up at something equivalent to Kx. So I have this correspondence which sort of swaps the free and the trivial ones around, and it's very clean.
But is a question,
yeah.
So it all happens actually in a multiple category if you're saying these equivalences are all quasi-isomorphic.
Yes,
right?
so I suppose at this point here, I should really start talking about the derived category,
right?
Because I'm identifying quasi-isomorphism.
Right, and that complex is just a two-term complex.
Yes.
It's one map between it of bimodules.
Yes.
Kx, K epsilon bimodules.
Yeah.
Okay. So you don't need, do you need to verify anything for that to be a complex?
I mean, the fact that it squares to 0 is trivial. I do have to make sure that somehow the differential and the algebra structure are compatible here, right?
Okay, that's the only thing you have to actually verify.
Yeah. Okay. Yes, so constructing this complex, and then I have to verify that, which is here easy, that this complex actually does resolve K0. So that's somehow taking well,
so
essentially.
That from Kx to K0, K0, and then,
Yeah, right. Essentially, what I'm saying here, I have two terms, but I want to divide this by the image of this map, which is exactly x, so I get K0, and I want to take the kernel of this map, but this map is an injection, so there's nothing here.
Okay.
So I'm done. So it's sort of a very friendly complex. Yeah.
Are we using the notation K epsilon or K epsilon over epsilon or not? Is it the same?
Right. So I guess this. So K epsilon over epsilon is somehow. I mean, maybe I'm also tempted to just write this as K or K0. But
okay.
that's.
Yeah, because on the word above it.
But K epsilon is.
This was an example of a module here, right? So K epsilon is my algebra. I always write like this.
Okay.
And then I have the module here, which is the one-dimensional module, but I get the coordinate epsilon. Yeah.
Okay.
And that's sort of the trivial module. Right? So I'm tempted to also call this K0. Right, but so far I'm just doing something very, very friendly. And the only subtle thing I've done is I've switched to the derived category and replaced identified quasi-isomorphic objects. So people who are unhappy with the derived category can still stop me and tell me to elaborate more or less or something. But essentially I'm just trying to relate category modules, and I'm saying that works better if I identify these quasi-isomorphic objects with their resolutions. However, in this correspondence, so this is clearly an injunction, it's also clearly not an equivalence. Right? The reason it's clearly not an equivalence is that I have these gadgets here, these Ka, the skyscrapers at those different points, and somehow this one is far too small, right? I can't see any of these skyscrapers as modules of the geo numbers, because there's not many modules of the geo numbers. And what's happening is, well, if I feed in Ka into my gadget, if I take Ka, and then just go through my computation here, what this actually ends up with is a module which looks like K epsilon, and K as a, well, this is a module over K epsilon. It sort of looks like a free module if I put the zero differential here, but I have a differential here which is A. So this is the same as the free module of rank 1 if A is 0, but if A is not 0, then this is some complex which A is a map from K to K. If A is not 0, this being a field, this is going to be injective and surjective. So this is going to be quasi-isomorphic to 0 if A is not 0. So this construction, this correspondence here, loses a lot of information about the modules of the polynomial algebra, right? Because I forget about somehow the fact that the line has points I can't see on the right hand side. And so there is, I mean, there was a workaround, which is to say, well, let's just restrict to graded modules, and to say there's an obvious grading where I just say, well, x could be in degree 1, and epsilon, I think, should be in degree -1. And then so I only look at modules which are graded, so I can't quote on x minus a because that's not homogeneous. A is an element of the field still at degree 0. X now has degree 1, so I kick these out. And so I do get the equivalent of categories. Which goes from the graded modules over kx. I also want these finitely generated to really only deal with these things, and will be bounded, so I can't have complexes which go off to infinity. And that is equivalent to the graded bounded derived category of k epsilon modules over fg. And in a way, I've cheated. I've just declared all of these kx to not be allowed because they're not graded.
Can I ask a question?
Yes.
So here in this equivalence, do we have two gradings coming from the grading of the modules and the differential, or are we seeing the graded modules as zero differential chain complexes?
Two different gradings. So,
okay.
I introduce an extra grading. So there's a new grading, which is independent of the homological grading. There's a new grading, it's called the Adams grading or the internal grading. So I have 2 degrees now. I have the grading by the generator, and I have the homological grading because I'm still looking at complexes.
Yeah. Okay. Thank you very much.
Yeah, and these two gradings are very important in the Koszul duality story. Right. And so this is an example. This is sort of the baby case of Koszul duality. So it's an equivalence of module categories over certain algebras which are Koszul dual to each other. And I'll clean this board.
So can I maybe quickly ask?
Sure.
The differential in the map in the complex consisting of 2 degrees.
Mm-hmm.
Why is that well defined?
Why this differential is well defined?
Yeah, just because k epsilon is k epsilon goes here, so it just seems like
It squares to 0.
Is that so?
Epsilon squares to 0.
Yes.
But here I'm just saying, essentially I'm saying I take my generator epsilon and I identify it with x here. So this epsilon, I mean this left-hand side modulus, the epsilon here is just a vector space generator,
So,
right?
so it's not as with the right, it's not compatible with the right action of k epsilon or something.
So I mean it is. Everything should be compatible, but so when I write this kx epsilon, I'm just saying this is a free module on kx with a generator that I call epsilon, and then this free generator is sent to x in kx. This thing together is an epsilon k epsilon module, where the module action now sends x here to x times epsilon here.
Yeah. Okay.
And the kx action just sends, multiplies here or here.
Okay.
Yeah. So this is sort of I have the generator, the differential, and the action going in different degrees, in different directions. Yeah.
Thank you.
So, and now let me give you the more general statement of classical Koszul duality, which it just saying, so for which algebras can I play this game of identifying these graded derived categories? So Koszul duality which maybe you can put some adjective in front of here. I guess one way is to say this, look at this quadratic Koszul duality. I mean, typically what people call, well, one of the things that you call Koszul duality is the statement, let me first generalize, essentially with the computation we've done, and a little bit of extra work, we get that the graded bounded derived category of the symmetric algebra on some vector space V is the same as the bounded graded derived category of the exterior algebra on V dual space. I'm just going to shift it in homological degree just to make things a little bit cleaner, and then again find general modules here. So this is somehow just saying I had the example of vector space in dimension 1, and now I can essentially do the same computation, so tensor it together and get the same example of an arbitrary finite dimensional vector space. And this generalizes further. What I really want to say is I take the graded modules over some algebra A, which has some good properties. And I'm going to say that this is the graded derived category of some dual algebra. And I can improve a little bit on the boundedness condition by putting arrows here. This arrow, somehow I want to say it's just not just bounded, but it might be bounded below. But I have to be a bit careful because I have two different gradings, the weight grading and the homological grading. So essentially this is some kind of triangle in the, right, there's some triangle going up here, some triangle going up there, triangle going down here in the plane of bigradings. Just some graded, some reasonably strong boundedness condition here and here, but not bounded. It is weaker than bounded. And where A is Koszul. And what does it mean? There's two different ways of saying it. One way, I guess the easiest way of saying it is A is quadratic. So it is of the form tensor algebra on some set of generators, divided out by some ideal of relations, and my relations live in the degree 2 part of my tensor algebra. So, for example, I can take my symmetric algebra on V as a tensor algebra on V divided out by AB equals BA, which is a quadratic relation. Or I get the exterior algebra by portioning out by AB plus BA, which is also a quadratic relation.
Why necessarily finite dimensional?
Why I'm looking at the finite and general modules?
Finite generator.
Yeah.
Well, why is it such a big importance?
I'm actually not. I think so. I think we need it, but I'm not entirely sure. Okay. I think I copied this from somewhere, and I haven't thought deeply about the classical base.
And for V as well.
I mean, V. Oh, well, V is a finite dimensional vector space.
Is that fair?
I mean, just trying to keep it.
Okay, that's fair.
But yeah,
I didn't know it was necessary.
It's possible.
But I think in general, derived motion and in theory, it's usually if you have an equivalence in the bounded derived categories of small, say finitely generated modules coherent sheaves, you also have the one of the big ones.
Okay.
Right. Yes. So these. Right. I mean, if I check that these are actually just the compact objects inside the bigger category.
Yeah.
Exactly.
But
you can extend.
You can probably extend.
Or at least
but there is
from
some.
The big one to the small one. I don't know the other.
Yeah. So I'm not claiming this is the most general statement. My whole point is going to be that one can generalize this way beyond these considerations. So I just want to sort of give the classical statement here, because it is somehow it's a very influential and powerful idea. So I should be quadratic, and then this Koszul dual A is just I take the quadratic algebra on the dual and I quotient out the orthogonal to R, right? So if R is a subspace of T squared V, then R perp is a subspace of T squared V dual. And so I can sort of naturally define this. And indeed, one can sort of, as an exercise for the reader, verify that this is exactly what happens from here to here. So the orthogonal to the commutator relation is exactly the anti-commutator relation. And this doesn't always work for any such thing. If somehow this pattern that I take my algebra together, they put on a suitable differential, and this should be quasi-isomorphic to the trivial module K, and it's going to be K is going to be a trivial module over A and over A shriek because they are these quadratic algebras, so I can just add V acts trivially, so I have a trivial module, which as a bimodule, K as a bimodule over A and A shriek, and essentially I want this to be a resolution of K0, and this is sort of generalized as Koszul complex. So this is a Koszul complex, and this is a Koszul dual. And there's other ways of describing it. There's a whole bunch of equivalent descriptions of being Koszul algebra. One important thing to mention is that instead of this very sort of description that depends on being quadratic, I can also look at A shriek as the X algebra of K with itself over A. And this I can form whenever I have K as an A module. And then it's going to be A shriek. It's going to give me Koszul duality. Essentially, if this is concentrated along the diagonal, there's a bi-grading, the X grading homological, and the weight grading. And if the weight grading and homological grading agree, and some of these terms are sort of pure on the diagonal, that is a Koszul condition, like it's computationally.
Wait, where is the weight grading? In K.
So the A is graded.
Ah, okay.
Right, so A, I assume is quadratic. It follows from this that it's quadratic as long as it's weighted. So you just need to have weight grading on A in terms of the generalises.
The discussion for the strong grading typicity with symmetric and stereo algebra. So I got this X grading and you got this.
Right, so in this case, somehow, so V is in weight grading 1, and then V dual is in weight grading -1. V is in homological grading 0. V dual is in shifted homological grading, so homological grading 1.
Right, okay. And then you do an extra grading on the tensor, just defined by the tensors. And
then if I look at the Koszul complex, for example, then it's sort of graded by adding the weight gradings and the homological gradings up.
Yeah.
I mean, there's no guarantee on pluses and minuses here, but the general pattern is the weight grading is always the same. The weight grading is determined by my generators, and the homological grading I can shift from here to here.
Right.
Because essentially I want K epsilon to also be the symmetric algebra on epsilon, but epsilon is an odd degree, and so symmetric means exterior. Right. So if epsilon is in degree 1, then the graded commutative, right, graded symmetric algebra, which has a degree 1, is an exterior algebra. So that's the situation is more symmetric than it looks. Yeah.
I think you said it, but I didn't hear it. The differential, how is it defined, or it's like canonical?
This one, it's canonical. If I try and write it down, I'm going to mix it up because I didn't write it down here. But I mean, it generalizes the one that I wrote down, the easiest case.
Yeah.
It's also like looks very similar to the Koszul complex for regular sequence. Essentially, there's a very natural differential there. But yeah, I'm going to get it wrong if I try and write it down explicitly. Okay, so this is somehow the classical Koszul duality story, which is very powerful. And essentially, when relating theorists they do some work and they realize that some algebra is Koszul, they're very excited because it tells them a lot about the representation theory of a Koszul algebra is very clean, sort of close to semi-simple in some sense. But this is very special, right? Because I say, well, I have to restrict myself to quadratic algebras. And there's plenty of algebras which are not quadratic, which are not inhomogeneous. I could have generators, I could have relations in different degrees between my generators, but I could have an algebra where x squared equals y. well, it's a bit boring, x squared equals x cubed equals yz square, whatever. I can have non-homogeneous relations to my algebras, but then they can't possibly be equivalent. And then I have this, well, this condition here, or this condition here, which is very strong on top of being quadratic. And then for all of that, I only get this correspondence of graded modules when maybe I want some general correspondence of derived categories. And so this is what people were concerned about and what was very cleanly solved by Positselski. Let me give you a, let me give you the wish list, and then tell you that indeed we get everything off our wish list. Right, so our wish list essentially says for any algebra, and because we are working in this, we already started introducing some shifts in our algebras there, so we probably want to work with DG algebras, right, which is just algebra objects and chain complexes. We want a Koszul dual algebra. And we want to identify their derived categories without any gradedness restrictions and boundedness restrictions. Not graded, derived categories, non-graded derived categories. And I guess we also want this to be involution on PG algebra, so that if I take the Koszul dual and I take the Koszul dual again, I get back where I started. Right, which is when I do, I guess when I do this, it's kind of clear. My first quadratic description, but when I think of the Koszul dual as being this exterior algebra, then there's sort of no guarantee that if I do that process twice, I get back where I started. In fact, it's often not going to be true. So this is what I want. And I can get everything I want at a price. What we get is I guess if we turn this into a co-wish list, we get everything we want. So for any DG algebra, there is a Koszul code, not code, a Koszul dual co-algebra. We can identify the co-derived category with the derived category. And this is, well, it's not a co-involution, but it's an equivalence of categories between algebras and co-algebras of a certain kind. Certain algebras and co-algebras. So, oh yeah, in fact, yes, this, you asked about V being finite dimensional here. Yes, it is important. I now remember that V being finite dimensional is important. And there's one reason for this is because somehow the natural Koszul dual is the co-algebra. And if V is finite dimensional, then this is invisible here. The exterior algebra is finite dimensional, and so co-algebra, the dual co-algebra is, I can go back and forth between the algebra and the co-algebra because it's finite dimensional. If V is infinite dimensional, then this algebra is going to be fundamentally different from the co-algebra. And the Koszul dual thing is the co-algebra, so this is going to be wrong. This is going to be false if V is infinite dimensional.
But if you would change, that's because you would like this exterior in there. If you would then change what this should be, you could go to infinite dimensional.
I have a correct, in this world, I don't have any finite functions here.
Okay.
So in this one, I can take the Koszul dual coalgebra,
Yeah.
which is some of the exterior coalgebra in the infinite dimensional space V.
Okay.
And then the coderived category of that is going to be equivalent to the derived category of the
Okay.
symmetric algebra on the infinite vector space.
Okay.
And yes, but this finite dimensionality is indeed important. This one I'm not entirely sure about, but this one,
Okay.
this one we need. Okay, so this should be an evolution, i.e. an equivalent categories between algebras and coalgebras. And I need some adjectives, but I don't need many. And let's see. Let's see how we do this for time. So let me first say that we are going to work with conipotent coalgebras, which just means that there is a unique group-like element. So there is a map K to C, which is induced by the unique group-like element. So del X is X tensor X. And then my coproduct in my coalgebra on C divided by K, C bar, is nilpotent as an operator. Sometimes I have a group-like element and I keep applying the coproduct, I'm never going to die. But once I divide out my group-like element, I can talk sensibly about the potency of the coproduct, and this is going to be the case. And so this is, right, for example, I can take K epsilon dual, and this has a coproduct which has epsilon star to epsilon star tensor 1 plus 1 tensor epsilon star, and it has a group-like element which is the 1. And if I divide out the 1, then my coproduct actually is already 0. So in particular, it's no problem. But also I could do something similar with some polynomial coalgebra, and there I have also x goes to x tensor 1 plus 1 tensor x. But now I also have something like x squared, which is something like this. And now if I quotient out by the 1, then this goes to x tensor x, but then I try it again, and then x goes to 0, x goes to 0. So this is just somehow many friendly coalgebras that you know are copotent. For any coalgebra, in copotent, I can talk about comodules, which is just a module, the dual of a module, so comodule n just has a map from M to N tensor C, dual to the map from A tensor M to M for a module. And I can talk about the category of all comodules. And the category of comodules, because everything here is DG, I could look at those up to quasi-isomorphism and form a derived category of comodules. However, that's somehow not the correct thing to do. It doesn't have as nice properties, so this goes back to Rivera, who said instead one can take C comodules, differential graded. I guess C can be a DG coalgebra. And I form the coderived category of C comodules. And that, which is somehow taking the homotopy category, as I normally would, I identify homotopic maps. And then I also kill all the objects which are coacyclic, which essentially means total complexes of short exact sequences, and also infinite direct sums of those. So I'm saying which objects should I kill in my homotopy category to get my derived category? Normally, I kill everything that is quasi-isomorphic. If I kill quasi, which is 0, everything that doesn't have homology. If I kill everything that doesn't have homology, in particular, I kill those little modules, co-modules, K goes to epsilon by multiplication with A. Well, this has zero homology, but this is not a total complex of a Schottky sequence. So these survive. So this is not equal to 0 in the co-derived category of K epsilon. I guess I've written it as a module, but I can dualize and then look at it as co-modules. So I have this co-derived category, which somehow sees more about the representations. What I now would like to do is I would define for an algebra a Koszul dual co-algebra. And this is the so-called just the bar construction, by which I mean here, so roughly I mean the self-tor of the trivial module over A. By roughly I mean it's going to be quasi-isomorphic to this, but because I'm getting suspicious of quasi-isomorphisms, I don't want to use this as my definition, and I want to write an explicit complex, explicit co-algebra. And this explicit co-algebra is, so A should be augmented. I'm going to make one assumption on my DG algebra. A is augmented, meaning I have a map from A to the ground field, which is a section of the unit. And then I can take A divided by K and call this A bar, and I take the tensor co-algebra, which is like the tensor algebra, but I have a co-algebra structure instead of an algebra structure. So the deconcatenation co-product over my ground field of A bar, which is A divided by the unit, or the kernel of the augmentation map. I put a shift of degree here, and I put some differential, and the differential is induced by the multiplication and differential in A. And so this is the bar construction. This is a co-algebra, because if you find it to be co-algebra, I have to check that my new differential is indeed a co-derivation. And this way I can associate to any augmented DG algebra a DG co-algebra. And once I've done that, I can compare the derived categories.
I have a bit of questions about this co-derived category.
Okay.
Is the category of co-modules abelian?
Yes.
Okay, so it's just finding a different model structure on this category of co-modules. So is this homotopy, the way the derived category is constructed?
Mm-hmm.
Is it like the homotopy? Can we find a model structure on this C co-mod that gives exactly this? Or is it always these two steps?
No, there is a model structure here. Yeah, this is a homotopy category of model structure.
Okay.
Yeah, one can do the same definition over algebras, and then it's actually not known as far as I'm aware. But there is a model structure.
That gives this.
That gives this, yeah. But for co-algebras, this is part of the model structure. Right, so here's the fact. And I'm going to tell you the more general theme it's a part of in a second, but just A module, the derived category of A module is equivalent to the co-derived category of B A modules. Well, so in particular, I can, BA is going to be equivalent in a suitable sense to the dual numbers if A is a polynomial algebra, but the co-derived category of the dual numbers has all of these elements that correspond to the skyscraper shapes on Kx. So I do get a large enough category to describe this DA mod. And
Sorry.
Yeah.
Could you describe the functor in using it, or?
The functor, yes. The functor is so if I have an A module, somehow A acts on some module n. I'm going to take AM, I'm going to tensor it over K with my module n, and then I'm going to use the action together with a canonical map between BA and A to define the differential here. So the differential is defined using action and let me get this right. There's a map from A to BA, and so I can use. Wait, there's a map from. Like this, yeah. There's a map from BA to A, which is. Yeah, which is not something wide, but yeah, which corresponds to the map that there's an identity map from BA to A, and because this is a coalgebra, it's sort of defined in terms of defining the image to A, it defines the whole map from BA to BA of coalgebras. So this map that's underlying the identity from BA to A allows me to go from here to here, then use the action, and so I twist the differential by this action. So this is one of the canonical elements, so sometimes I can. One way of writing this is just like with a little tau for the twist here. Yeah, and so this, I guess this correspondence here, the Tor should, right, that's the dual of the X group that was the classical Koszul dual. So that's why this really is very close to the classical Koszul story, but it is different because I'm talking about coalgebras now, I'm talking about coalgebras categories now. But the advantage is that things are true now. And dually, I can define from C, I go to omega C, which is going to be the tensor algebra on C shifted by -1 against C bar being the quotient by the augmentation, co-augmentation, and I have a differential which comes from the co-product and the differential of C. And so this is a math function that goes the other way. And there's one more thing to specify before I state the theorem that I want to state at the end of the first part, which is what if A is not augmented? So we've defined this cotensor algebra here, cotensor coalgebra here, by using A mod K or the kernel of the augmentation now. If I'm not augmented, I can still talk about A mod K, right? That's still a reasonable space here. I can still look at this. And I can still try and induce a map here by the differential and the multiplication, but now on A mod K, these are not necessarily well defined, right? Because the differential doesn't descend to A mod K. I have to choose a splitting, which I can do, which is not going to be compatible with the algebra structure. So A is K plus A bar. And now we can define D again from the multiplication of the differential, but D squared is no longer 0. And instead, D squared is going to be some term which is dependent on the multiplication differential of A, and it's called curvature. So whenever I have something which looks like homological algebra, except that D squared is not 0, I hope that D squared is at least curvature. And this is really a lot like the curvature in differential geometry, in that it arises from something not squaring to 0, but it does have some good properties. It's not just a random object which could arise in that place, right? Not every random endomorphism value 2 form can be curvature of a connection. And so this also satisfies some good properties. So instead, D squared of C is now a co-commutator of C with some element H, where H goes from the degree 2 part to the ground field. And this is the curvature. And it's closed. It has some good properties arising. And I'm not going to spell out in great detail. I'm going to have to look at some compatibilities and things. But I think now I'm just going to tell you the theorem due to Positselski, which is somehow the cleanest form of non-homogeneous Koszul duality, which says that there exists a junction from curved coalgebras, which are conal-potent, and which have an artificial final element, which you shouldn't worry about. And this is this omega, and the adjoint is our bar construction, and this goes to the G algebras. And I can do a subcategory of augmented DG algebras and restrict this to a correspondence with DG algebras, still conal-potent. This is equivalence with suitable model structures. And in particular, suitable on the right-hand side means the usual one. So if you're familiar with model theory, model category theory, then there is a canonical model category structure in DG algebras to do homotopy theory of algebras, which you do, for example, in rational homotopy theory. And it's exactly this model structure on the right-hand side. And then some more complicated one on the left-hand side. Which one can characterize in terms of filtered quasi-isomorphisms. And D of A mod, so the derived category here, is the same as the co-derived category of BA co-mod, and vice versa. So D of omega C modules is the same as D co of C co-modules. If C is a curved co-algebra, and if A is a DG algebra. So this is somehow Koszul duality without any assumptions, either on the algebra or on the category of modules.
It is a Koszul potency, right? Koszul potency is always there.
Yes, yes. So I'm saying there's no assumption on the algebra, right? The algebra side is all DG algebras, but then on this side it looks a bit weirder, right? Because there's a Koszul potency assumption, and I have to admit curvature, right? So this is somehow, yeah, this is not just the category of all DG algebras. But if I'm trying to understand DG algebras, I'm saying I can give you precisely kind of co-algebras corresponding. And let me just give you two examples. And then we can have tea. So if I take the singular chains on a topological space, then I have a co-algebra structure on that. And I can take the co-bar construction on this, and this is where the co-bar construction comes from. Originally, this was Adams' way of making the loop space construction algebraic. This is Adams in the simply connected case in the 50s, and then in the late 20-teens, Rivera and Julian did this for all topological spaces, including the non-simply connected ones. So there is this loop space gives a topological interpretation of the co-bar construction. And now my statement that the co-derived category of the co-algebra is equivalent to the derived category of chains of the loop space. And now the derived category of chains of the loop space is somehow topologically, this is just the category of all infinity local systems on X. So these are just somehow sheaves on X, which are whose cohomology sheaves are locally constant sheaves. So it's a very natural variable of the space, and I can describe it in terms of C star of X. And this is a good example where, like, somehow if you first meet chains, when you first meet chains on X, you meet them in order to take cohomology or homology and determine the topology of the space. When you do that, you lose a lot of information about the fundamental group, right? Because many spaces of interesting fundamental group but they don't have interesting H1. Nevertheless, if we don't take homology here, if we look at this in the larger category of coalgebras, then this co-derived category remembers a lot of information about the fundamental group. All the representations are still in here. So that is sort of one of the interesting things, which is co-derived categories are the richer invariant of the object here. Or more algebraically, if I take the Calabi-Yau complex of the Lie algebra, then the co-bar construction of that is going to give me the universal developing algebra of the Lie algebra. Yes, right. So this is the co-algebra. I look at this as an algebra, and so the derived category of the universal developing algebra, which is nothing but the derived category of the Lie algebra, is the same as this co-derived category of the Calabi-Yau complex. And if you look at formal deformation theory, like deformation theory in Lurie, he is interested in this category in a slightly different. He gets as int co of the Calabi-Yau complex. So that's in this example, that's just a different category, different calculation of the same category.
Sorry, could you repeat the last line, please?
So last is from right to left. I'm saying the derived category of the universal developing algebra of G is the co-derived category of the chain co-algebra of the Calabi-Yau complex. And this is also sometimes considered as the so-called incoherent modules over the Calabi-Yau complex. And this is just, if you've seen this before, you should go, aha. If you haven't seen it before, ignore it. But like the category of incoherent sheaves within algebra geometry is sometimes used as a refinement of the category of quasi-coherent sheaves. And it's a similar kind of refinement to this one.
In this derived co-derived, does it see also all the higher homotopy groups, or just the first because we take one as the loop space?
It also sees the higher stuff. I mean, it sees what it literally sees. It sees all the representations of the fundamental group, and it sees all the cohomologies of the coefficients. So it doesn't literally see the higher homotopy groups, but you can reconstruct. Right? I mean, in particular, if I have a map here which induces an equivalence of co-derived categories, right? A map from X to Y inducing this equivalent here, that means it induces an equivalence here. And so if I have a map between connected spaces and the derived categories of these algebras are the same, and I have a map which on the algebras that actually all must be the same. So I can actually detect weak equivalences using this. Yes, so this is what I wanted to say in the first part. Thanks. So very happy to be here. And we ended the first part of the talk with this very nice correspondence, duality, and we want to generalize this further. Right, because it seemed like we went very far by going to an arbitrary DG algebra, but the DG algebra is nothing but a DG category with one object. So we can look at DG categories instead of DG algebras, and see what that gives us, and if that sort of if this correspondence still works, if we get a Koszul dual of a category, and we can, and the key is to say that an algebra is to turn categories into algebras, so DG category is somehow a monoid in bicomodules. Over a co-semisimple coalgebra, over a varying co-semisimple coalgebra. What does that mean? So I take my DG category D and I associate to it a vector space on the elements of D, on the objects of D, and I give this a coalgebra structure, a co-semisimple coalgebra structure, but it's saying every element, every object here corresponds to a group-like element. So somehow I have D goes to D tensor D, is my coalgebra structure, and I'm going to call this D0. This coalgebra, and then I also have my my homes, and I'm just going to take the direct sum over all the homes in D from D to D prime, and this I'm going to call VD. Right, so my DG category should be small for this to make sense. I take all the homes together. It's a vector space, or it's a DG, it's a chain complex, but it has another structure, and it has indeed does have a bicomodule structure over D0. So this essentially means if I have some F in VD, I'm going to send it to the codomain of F, tensor F plus F tensor the domain of F. Right, so codomain of F is an object that encodes for me an element in here. In D0, right, so this is in D0 tensor VD, and this is in VD tensor D0. And so this is a comodule structure on the left and on the right. And so this turns this into a bicomodule.
This coalgebra is a vector space as its basis objects of D, right?
Yeah.
It's not,
Yeah, it's a yeah. So the vector space basis, and on each basis element, I tell you what the coproduct is, so you know the coproduct everywhere. So in a way, this is just a clever way of encoding the fact that I have domains and codomains. And then, so this observation apparently goes back to Aguilar, which Aaron told me about, which I didn't know, and then rediscovered it. We rediscovered it a while later. And the other thing is it's a monoid because I can compose maps, but I can only compose maps if domain and codomain line up. And that's exactly saying that my my composition from DD prime tensor D prime D double prime to DD double prime induces a map which goes from VD, and not VD tensor VD, but VD cotensor over D0 with VD to VD, and this thing here, this cotensor, is just by definition the kernel of VD tensor VD goes to VD tensor D0 tensor VD. So I can, or the equalizer, if you will, of the left and right action, coaction here. So much like the tensor product is usually a quotient of the two multiplications that the modules have, so the cotensor is the kernel of comparing the two different coactions I have here. And somehow the fact that I have composition exactly if source and target agree, or this target and source agree, is the same as saying I have a comonoid multiplication here. I have a monoid structure for the cotensor product here. So these are monoids in bicomodules over co-semisimple coalgebras. And you don't have a fixed co-semisimple coalgebra, but it varies with my set of objects. So this is just a weird way of encoding a category. Well, it works for any linear category, in particular for DG categories. But once I have that, I can say, since Koszul duality naturally, while it goes between monoids and comonoids, I can just go through this construction now in this bicomodule situation. So we want to define my new bar construction from monoids in bicomodules, which is sometimes called semi-algebras, to comonoids in bicomodules. And a comonoid in bicomodules is actually just a kind of coalgebra, right? Because it's somehow, it goes in the same direction. I don't have to have this slightly awkward definition anymore. In fact, what I get when I do this, so BD, I can define as the cotensor coalgebra relative to D0, relative to this co-semi-simple coalgebra of BD. I throw out the units, I shift it by 1, and I define a differential and a curvature using the composition and the differential. And what kind of object this is it's a pointed curve coalgebra. So it's a coalgebra which with the differential and the curvature such that the co-radical, which is the maximal co-semi-simple coalgebra, I'm going to call this C0, is a direct sum of copies of the ground field. So that essentially this has exactly this form. Generator goes to generate the tensor itself. It's just a bunch of group-like elements added together. Right, so there are other co-semi-simple coalgebras you could define that would not have this form, but if the maximal co-semi-simple has this form, right, and then by definition, delta, the co-product is nilpotent on C divided by C naught. And then I need compatibilities, and somehow the differential and the curvature and the co-radical embedding into C, this needs to be split, and this needs to be compatible. And I'm not going to spell this all out, it's not going to be very instructive. But there is a fair number of compatibilities. But essentially, it's just a curve coalgebra, which, if it was co-nilpotent, the co-radical would just be one copy of K, one group-like element. And here I have some set of group-like elements. If I divide out the set of group-like elements, I get something nilpotent. And then I want to have differential curvature and things to be compatible. And this inclusion of the co-radical, if this was just one element, if I was in the co-nilpotent case, then the inclusion of the group-like element would be split because this map would just be the co-unit. And now I have to demand that this map exists, or that the co-unit factors through the C naught as some extra data. But it doesn't matter too much. I'm just saying it's a kind of curved coalgebra that I get on the other side. And with that, I can state the theorem that says there is again a equivalence of module categories, of model categories. And it's suitable again, but again, the one DG category is going to be the one you first think of. Independently of which one you first thought of, there's two reasonable ones you could first think of. They both work. Model categories being from DG cat prime. I have to do one small modification of my DG categories, which doesn't matter for the model category much. Just throw out some objects which are which equivalent to 0 anyways. And pointed curve coalgebras with an artificial finite element. And this I'm going to call omega again. So this is an equivalence. Here I could use the Dwyer-Kahn model structure with quasi-equivalences between model categories, or I could use the Morita model structure, and then I get localization here as well. So if you want, I have two different model equivalences depending on which model structure I start with on DG categories. and then the derived category of omega c, or the derived category of the DG category, which is just functors from the DG category to chain complexes with some model structure, with some derived category, is going to be the co-derived category of the dual coalgebra. And if I similarly, if I start with a coalgebra, I can apply omega and get a DG category, and that derived category is going to be equivalent. Right? These are equivalents of derived categories, but they also come from closed equivalences of the model categories. Yeah, so this is somehow the key statement. The proof works very similarly to the one object case. In that somehow, if we think of fundamentally what we're doing is we're showing that we have a junction here, and then we show that actually this junction is equivalent of categories. It's equivalent equivalence. The second part, once we have the junction, we're going to transfer the model structure from here anyways, because how else are we going to construct the model structure here, if not by transferring it from this other side? To be fair, in the one object case, Positselski writes this down by hand in a weird way, but the more, I mean, it's not clear how to generalize that, and it is clear how to generalize the transfer. So the real key to get started is this adjunction. And the idea of the adjunction is to say, well, if I look at hom in DG cat, say from omega c to d, so roughly speaking, this is some kind of free construction. So this is going to be given by some kind of hom from C bar to D. By saying this is some free DG category on some set of generators C, so if I define my map of the set of generators, I get this. And dually, if I look in kind of coalgebras, then this bar construct is some kind of co-free coalgebra. And so the map into the bar construction is also going to tell by some map from C to D. So there is some version of maps from C to D which works in both ways. And the only thing is I have to be a bit careful about the fact that I have a C bar here. That is not quite maps from C to D because, well, I have to just be a bit careful with bookkeeping. And then I have, of course, compatibility with differentials and curvatures here. And this is expressed by saying that I take Maurer-Cartan elements in this thing. This thing being hom from a co-algebra to a category. And so the this algebraic structure of this is a convolution category, a convolution product. And this is a non-unital category, convolution category. And this corresponds exactly what one does for what one would do in the one object case, and then sort of it becomes a bit cleaner or a bit conceptually easier. And but one can do it as well in the multi-object case with some care. I guess proof ingredient. Well, it's not the whole proof. There's a lot of other things happening, but some of that's what gets you started. The fact that really we have something built on the tensor and the cotensor product, so it's going to be determined on maps between the underlying things. And yeah, maybe questions while I see the next board.
star meaning? Point. No, what is the star meaning?
The lower star means I add a final object artificially. Because of the way that maps work between curved coalgebras, there can't be a final object. You have to add a final object by hand.
To the category.
Yeah. And that, which is the thing that corresponds to the 0 DG category.
Yeah.
Which is one object and only the 0 morphism, as opposed to the empty DG category, which corresponds to the 0 coalgebra. The 0 coalgebra is a curved coalgebra, and it's initial, but it's not terminal, and it can't be. Yeah, with the way the definition works, that you just can't have a terminal object. One weird effect, which I had overlooked for several years until talking to Arne a few months ago, is that the model structure on the right-hand side, every object is cofibrant except for star. Star is not cofibrant. I've not seen this before, where you have a model category and every object but one is cofibrant. But it has to be. It's sort of it's forced. Yeah, not entirely sure whether Positselski's model. He defines slightly model structure. Not entirely sure it's correct. So this in particular tells me that curved coalgebras are a model for DG categories, right? In the sense that they are coequivalent. And one way of thinking about this maybe is to say, if we look at quasi-categories, like just the simplicial sets with the Joyal model structure, or which nowadays many people just call infinity categories, and you say that this has another model which is simplicial categories, but there's this classical way of having the coherent nerve functor here, and then there's this weird functor going the other direction, that is sort of a simplicial category, from a strictification functor from quasi-categories to simplicial categories. And if I linearize this here by taking the first thing is to simplicial K categories and then to DG categories with both Kahn. And if I take my simplicial set here, with my quasi-category, which is just a simplicial set considering a certain model structure, and I linearize that, I get a linear simplicial set. I get the diagonal gives me a coalgebra structure. I take dot Kahn here as well, and I get a pointed coalgebra. And in fact, I have to modify things a little bit, and this slight modification here introduces a curvature term, a small curvature term. If I just take the naive chain coalgebra of my simplicial set here, it's not going to be pointed and it's not going to be compatible with the splitting in the right way. It's kind of a bit stupid, but you can fix it by introducing some mild curvature. And then here I have my Bar-Koban construction, and this diagram homotopy means. Well, so I have an equivalence of model categories here and here, and I have my linearization functors here, and so I can really think of the bar construction as being like the coherent nerve that takes me from this very explicitly defined but formally awkward DG category or simplicial category to the somehow sleeker world of infinity cats. And similarly, these curved coalgebras live on the infinity category side of things.
And there are no issues with these negatively graded, because in general, these S-cat and DG-cat are more like positively graded.
Right. So, I mean, here I have this inclusion into all DG categories, right? And similarly, inside curved coalgebras, I could be negatively graded, and this equivalence still works. So, yeah, there's no obstacle to.
So the curved coalgebras are bigger. You expect them to be even a multi-category to be.
Right. I mean, these are very different, right? So in a way, from here to here, I forget law structure by linearizing, and then I include in a bigger thing. because I have a lot of curved quadrats which don't come from simple sets, right?
Okay.
One for degree reasons, but also for other reasons, right? There could be all sorts of other coalgebras, right? Not, I mean, right, if you think about this side here, if I think of the one-object case, right, then this would be from simplicial sets to DG algebras. I can build a DG algebra from a simplicial set, but I'm not going to get all the DG algebras that way.
Up to
Right.
multiply, don't you expect?
From simplicial algebras, right? But not all,
algebras, okay.
right? But anyway, my co-product here has to come from the diagonal map, right?
Ah, there, yeah.
So that's very right. My simplicial monoid here, but if these are simplicial monoids going to be G algebras, but not every algebra sort of the product doesn't have to come from the product defined on the let's say space elements to base elements, if you will.
Right. On the category level, but I'm always fearful if you do on the multiply level how much.
We don't expect these vertical maps to be equivalences in any kind of model way either.
But you restrict these DG cat to positively graded DG cats, neither?
No, but
No.
then there's still
Not even.
linearity versus non-linear.
Ah, okay, yeah, okay.
But
Sorry,
even-
the linearity is okay.
Right, and the linearity also gives you more room for your products to go, right?
Okay, yeah, this is nice.
Yeah, like the map from monoids to rings, right?
Yeah. I thought this,
Right, and so somehow, and in a way, so the commutativity, if you look at the one-object case of this commutativity, that actually gives you another way of proving the Adams result in the simply connected case, that in the non-simply connected case, that somehow, like if you unravel this a little bit, for one object, you have somehow here a loop space construction from here to here, and so the loop space and the linearization and the linearization of the loop space. So you somehow corollary of this is another proof that C omega k is omega C k for k. And the fact, maybe another way of looking at it, that this is sort of not completely crazy, is that the nerve and the bar construction are kind of similar on the face of it. Both nerve and bar construction means, well, I take things, right, I take composable things, like for the nerve, I connect together composable morphisms, and in the bar construction, I have this iterated tensor product over D naught, which means that my tensors also have to have this compatibility, which is like the composability in the nerve. So they look very similar, of course, then they're defined very differently, and one has to do some work, but it shouldn't be completely surprising that the nerve and the bar construction are related. The bar construction is like a linearized version of the nerve in some sense. Yeah. Okay, so now I've claimed that my curved coalgebras live on this side where things are sort of formally nice, even if they're less intuitive. And so one way of proving that is to say that curved coalgebras pointed, they form a monoidal model category. So I guess this is another theorem with Andre. So on DG categories, I can tensor them together. I can look at Hom spaces, but the tensoring together is not compatible with the model structure, which is very annoying, and which makes the correct derived Hom of DG categories difficult. But in curved coalgebras, I can tensor them together, and somehow C tensor C prime, I can define it naively. And because my elements are all cofibrant, and my cofibrants are just injections, this is equivalent. Somehow, by construction, it's going to send injectives to ejectives. And one can, I mean, it's a little bit, we need a little bit more to be bi-equivalent, but it all follows quite naturally. Actually, there's one, I mean, we need a bit of an ingredient, but anyways, this is indeed equivalent bifunctor. And so there is a monoidal model structure. And the Hom between two coalgebras, one can also define. So the Hom is defined in a more complicated way. And in fact, I'm going to define it from C to BD and then extended by limits. And so this is going to use my convolution category from C to D. And then I'm going to take some Maracaton DG category, some DG category of Maracaton elements. And then this is a DG category. Now I'm going to take the bar construction, we're going to call algebra. And somehow this works and provides me a functor which is adjoint to this and which is another clone bifunctor. And this gives me a monoidal model structure. And the map omega from curved coalgebras to DG categories is quasi-strong monoidal. So it's monoidal, it's lax monoidal, and in the homotopy category, it is strong monoidal. So I have this nice model structure here, which is compatible with a nice closed monoidal structure, and then I'm saying the comparison map here is compatible with that, at least on the level of homotopy categories. And what that buys me is that while DG cat is still not and will never be a monoidal model category, it is a curved coalgebra model category. So much like there's a lot of simplicial model categories that are enriched over simplicial sets, so DG categories are enriched over curved coalgebras. And while the monoidal structure on DG cat is not compatible with the model structure, is not equivalent, the enrichment and the tensoring and co-tensoring which also exist are all equivalent. So in fact, DG cat is a curved coalgebra model structure. So that means I can sort of take two DG categories and I can take their home in curved coalgebras. I can take a DG category and a curved coalgebra and tensor them together. And I can do DG category and take a power set, a power object, or a cotensor also in DG cat. And these are all equivalent functors. So I have an enrichment, I have a tensoring, I have a cotensoring. So in some sense, I want to think of DG cat as a torso over curved coalgebras. It doesn't have quite the same nice property as curved coalgebras, but the action of curved coalgebras is very nice. And the action, all these actions are as nice as one could ask for.
What was the argument that illustrates or shows that the model structure on DG categories cannot be monoidal?
Right. So the issue is that because the cofibrations are kind of special and they're free essentially, and so if I take two generating cofibrations and I tensor them together, is this gonna work? Well, this might be too simple.
Yeah, it's also all right.
But or in DG algebras. But if I tensor together the cofibrant DG algebra, like a free DG algebra, one generator, tensor together with another one, I get a commutative algebra, which is not free. It's not going to be cofibrant. Essentially, that is the key. The same in DG algebras as in categories. That because the cofibrations are special, and tensoring things together introduces extra relations, which are not allowed for the cofibrant objects.
I think in this case, you can think like a two-object DG category with a single 0 and 3.
Yeah.
It's covariant, the tensor product with itself.
But I did that claim that this shows that there cannot be a monoidal. I don't know. Yes, because of
With distance effect.
Yes.
with distance.
Yeah.
Okay, yes.
Yes. And somehow, I mean, and that's sort of clearly the national tensor product, but that it's not compatible.
Mhm.
It's sort of funny that you have a nice model structure description on the DGCAT, and then you transfer it to the coalgebra side, and then you have nice tensor, and you push it back.
Yeah.
It's just like you steal one from the other and bring it back to it.
Indeed. Yeah, let's do exactly that. Let's steal the good structure from the coalgebras, and let's compute our hom in DG categories. So I know that this is not going to be just the derived functor of the internal hom functor, but these compatibilities all tell me that if I want to compute this, actually it is good enough to compute the internal hom in coalgebras and then transfer it back to DG categories. So this is going to be, well, so our hom is going to make sense, right? Even if it's not, if I don't have the model structure, right? There's going to be an adjoint on the homotopy level to the tensor product. And this is going to be equivalent to taking the coalgebra hom from BD to BD prime. And this, remembered, was, and then this is a coalgebra, so now we apply omega. But this, by definition, was B of MC. Omega B cancels out. So I get MC. And then this was BD D prime anyways, because I had only defined this if the second thing is a bar construction of something. And so the alpha, so if I look at this, and if I unravel what this means, I look at maps from BD to D prime, and that satisfies some condition of the differential. And the BD is going to be this cotensor construction, which gets like arbitrary strings of maps. So this is the same as A infinity maps. And so this is one way of proving this, what Kontsevich claimed confidently many years ago, and was only really proven by Canonico, Ornari, and Sperari in 2019, I think, that A infinity maps give a correct internal homogeneity categories. And here it sort of drops out reasonably nicely out of this duality of the coalgebras.
You don't need to resolve either D or D prime because you use this bar.
Right. So yes, I mean, so this, because every DG category is fibrant, BD prime is also going to be fibrant.
Okay.
So I don't have to resolve this, and everything is cofibrant anyways.
Ah, okay.
Yeah. So the resolvement is actually taken care of by the D here. Okay. So this is most of what I wanted to say on existing work. Now I can like talk for 3 minutes about work in progress. Which is a reasonable thing to do. Well, I have to say Calabi-Yau for all, right? So blame him that I'm going to talk for 3 more minutes. Right, so we can transfer more structure, right? So DG category is Calabi-Yau, or has, let's stick with the weak n Calabi-Yau structure if there exists some class in Oxford homology of my DG category such that the induced map from D shriek to D is a weak equivalence of D tensity of modules. So this is what category theorists made of the geometric notion of Calabi-Yau. Key example, if D is the derived category of a Calabi-Yau variety, then HHN is exactly the top homology. My class omega is going to exactly induce such an equivalence of categories here. So the Calabi-Yau structure on categories or on algebras, right? This category could have one object, and this also makes a lot of sense. It's sort of a generalization of this geometric notion that is very fruitful. And so this has a weak Calabi-Yau structure is nominative, and so this is joint work in progress with Rivera. If the coalgebra has a weak Calabi-Yau structure, and one wants to actually put another word here, either smooth or left, and we put a word here which is either proper or right, depending on taste, which is i.e., so there exists some class in Koszul homology of this coalgebra BD, and this induces a map from BD dual to BD as BD comodules by comodules. So we're just saying we can translate this to this. The beauty of this is that, so this reconstruction here is some R hom from D to D tends to D as D tends to D modules. It's quite complicated a priori. This dual is an honest dual of the underlying vector space. So this is somehow a much nicer object. I have to, though, then compare these not as vector spaces, but as bicomodules. And in my last minute, I'm going to give you one example of what this, when you have this in the, well, it's out in the wild. Do you want the topological spaces or Lie algebras? Anybody have any preference? Quickly, Lie algebras. So UG, e.g. UG has an n Calabi-Yau structure where n is the dimension of G and G is finite dimensional and also unimodular. So, for example, it's semi simple, but it could be more complicated. And so that means that the Koszul dual, which we talked about earlier, C star of G, also has an n Calabi-Yau structure. So that means C star G is equivalent to C lower star G with a shift. There was a great shift there. There's shifts everywhere. Too late for a shift over there. But not just equivalence, but somehow in the stronger bicomodule sense. And what corresponds to this, one way of testing this bicomodule equivalence is tensoring with modules. And so what is the case here is I can put an arbitrary module here. And this is still true. And this is probability with coefficients for the algebra. For, which, what did I say the algebra should satisfy? It should be, it was unimodular. So we have two classical results about Lie algebras, whether they satisfy this probability of their cohomology, and that there is a Calabi-Yau structure in the universal developing algebra. And essentially what they say is that they are really just two sides of the same coin via Koszul duality. And now